Hi, welcome to VC Video 10.4e Part 1, Lemniscates and Spirals, and an Introduction to Tangent Lines, Horizontal, Vertical, and Other.
On the calculator, I just want you to realize that there really is a vertical asymptote here, it's just that the calculator cannot draw it. So be careful about that. Lemniscates. So lemniscates are basically the infinity symbol. The ones we'll be looking at will either be horizontal, vertical, or will cut the first and third or second and fourth quadrants symmetrically. So the way they look is they are fairly easily recognizable because they will start with r squared and then equals a squared, a being constant, either the sine of 2 theta or the cosine of 2 theta. So here's an example. Now if you did want to graph it on the calculator, of course you do have to isolate r, so you would have to do plus or minus, in our case, plus or minus 3. So you'd start with r1 equals 3 square root of sine 2 theta, and then your easiest thing to do would be to let r2 equal negative r1 of theta. Okay, so how do we handle these? We're going to make a table. Now be careful, because the angle is growing twice as fast, you're going to have to plug in angles that are half of what you're used to plugging in. So instead of 0, pi over 2, pi, 3 pi over 2, you're going to do 0, half of 2 pi over 2, half of pi, and half of 3 pi over 2. That way, when you multiply them by 2, you will get the sine of 0 is 0. 9 times 0 is 0. R squared equals 0 means r equals 0, which is the pole. When you plug in pi over 2, this will become pi, when you plug in pi over 4, this will become pi over 2. The sine of pi over 2 is 1, so you get r squared equals 9 times 1, which means r is plus or minus 3. And then same thing here, you'll get pi, you'll get 0. Here you'll plug in 3 pi over 4, double it, and you'll get 3 pi over 2. The sign of that is negative 1. You'll get r squared equals negative 9, which of course makes no sense at all. Okay, so we do have the pole, and we do have these 2 points, 3 comma pi over 4 and negative 3 comma pi over 4, so you can easily see that it is in the first and third quadrants. Now, as far as how fat or skinny each of these loops or petals are, if you want to call them petals, we could find the tangents at the pole. So if you remember, we take our equation, we replace r by 0, and we solve. Now, in this particular case, we get sine of 2 theta equals 0, because we divide both sides by 9. And when is the sine equal to 0? Well, when the angle, which is 2 pi, is 0 pi, 2 pi, 3 pi, dividing everything by 2, you find out that you have a tangent at the pole of theta equals 0, and then another one of theta equals pi over 2. As soon as you get to theta equals pi, you're repeating them. So they are quite fat, which means as it comes down here, when it gets close to the pole, it's actually almost vertical right here. Okay, then we're going to look at spirals. Now, spirals don't have any trig in them whatsoever. So the simplest spiral is r equals theta, there's r equals e to the theta, there's r equals 1 over theta. Now, since there's no trig, you're going to want to at least go from negative 10 to 10 for your theta min, your theta max. If you do r equals theta and you leave it at 0.28, 0 to 6.28, that's all you'll get. You can kind of convince yourself that the graph looks the way it does if you plug in various values here. The r is equal to the theta, so if you express each of these as a decimal, you'll see that you will get this shape. Very hard to graph by hand. R equals 1 over theta. Of course, this does not go through the pole because theta, 0 equals 1 over theta is impossible. And you would really use a calculator to draw this. The pole is not on the graph, which is kind of interesting because it looks like it's going to just kind of spiral in and eventually hit the pole. It spirals in forever. So the graph approaches the pole without ever touching it if you did it on the calculator. Although this is an old TI-89, this is more or less what it would look like. Okay, in exercises 47 through 56, use a graphing utility, which is your TI, to graph the polar equation. And we have already talked about this in class. But the smooth graph, and you need to understand this for later, a smooth graph has no sharp turns. So, for example, Let me just draw one for you. Let's just do this and this. If I was, I'm trying to use my finger here to do this. Let's do that. Let's say you had something that looked like, I don't know, something that looked like that. No, she doesn't like that one, too tall. No, actually, I'd rather a cardioid. Okay, let's see if I can draw this. Something like that. What you have going on right here is you have a sharp turn, because notice it comes down and then there's a sharp turn. So you would never want to go past this. You would never want to go 0 to pi, because you're passing by a place that's not differentiable. Okay, you don't really need to know how to find out where the graph is smooth, but you should be able to look at the picture and get a sense of that. Okay, tangent lines to a polar curve, as opposed to talking about the tangent lines to the curve and those lines go through the pole. Now we're going to talk about find the slope of the tangent line at the given point r theta, find the points of horizontal and vertical tangency. Okay, so remember that the slope of a line is always dy over dx, right? Always, always, always dy over dx. Now, but our function is going to be a function of theta. So if you remember, and this is going to be when we used to do parametric, our dy dx was dy dt over dx dt. So what's going to happen now, which should make perfect sense to you, is that our dy dx should be dy d theta over dx d theta. If you multiplied by the reciprocal, the d thetas would cancel. So what you're going to have to do in order to find the slope of this tangent line, you need x and y both in terms of theta. The only way to find dy d theta is if you have y in terms of theta. The only way to find dx d theta is if you have x in terms of theta. And you're going to be given a function of r is a function of theta. So here's an example. You have r equals 2 cos theta. You are going to have to rewrite that as a set of parametric equations. X equals r cos theta, y equals r sine theta. So the r, of course, is what we have right here, 2 cos theta. So I end up with x equals 2 cos theta times cos theta, and y equals 2 cos theta times sine theta. Now this, of course, is 2 cosine squared theta. This, if you recognize it, is the sine of 2 theta. So what we have is we have x equals 2 times cosine of theta squared. We have y equals the sine of 2 theta. So the slope of the tangent line to our function at the given point is dy dx, which is dy d theta over dx d theta, which dy d theta, as you can see from here, is the cosine of 2 theta times 2. dx d theta is 4 times the cosine of theta to the power of 1 times the derivative of cosine, which is negative sine. You're now going to evaluate that at theta equals pi, so I go through and replace all the thetas by pi. So the cosine of 2 pi is 1, the cosine of pi is negative 1, the sine of pi is 0. I find out that at pi, I have ask you to do it at pi. Why am I doing it? Oh, yeah. Oh, at the given point. Yeah, and the given point here, this is the question right here. And the given point is negative 2 comma pi. So at pi, we end up with our slope of our tangent line does not exist, which means it's a vertical tangent line or a sharp turn. If we were to look at the actual equation they gave us, and you should know by now that it is a circle symmetric with respect to the horizontal axis, tangent to the vertical axis, and the radius is 1, which is half of 2, the diameter is 2. So it would look like this, or you could put it in rectangular form, and you will see that we have a vertical tangent line at negative 2 pi.